Hello everyone, in this video I'm going to talk about the divide and conquer approach when we're trying to solve computer problems. So especially in this video I'm going to talk about cases that the divide and conquer actually is not a good solution. I'm going to provide some examples of some problems. Maybe the very famous one is the Fibonacci sequence. And I'm going to show that one case or one solution of to this problem using divide and conquer, and I'm going to show why it's not working. And also at the end, I'm going to talk about when and when not to use the divide and conquer approach. So let's together review the Fibonacci sequence. As you remember, or you may have watched my other videos. If you have not, I will suggest you to watch other videos that is dedicated to the Fibonacci sequence. The Fibonacci sequence started with two numbers, some textbooks might use 0 and 1 as the first two numbers. Some others use the first two. At the end, it doesn't matter. There's going to be the same sequence. And then each number is generated by the addition of the last two numbers. So 1 and 1 are going to be 2, and 2 plus 1 are going to be 3, 5, 8, 13, 21, 34, and so on. So that's how the Fibonacci sequence is created. Again, it's a very famous sequence, like has been seen in the nature a lot, and there are some very good interesting features of this sequence. So let's see that how we can actually find the Fibonacci of a number. So the Fibonacci, and I'm going to write maybe a function, a recursive function. Again, you can watch my other videos about recursive functions. So let's say we're going to write the recursive function, let's call it fib, and for a number n. As we said, the Fibonacci of n, or the nth number in the sequence, is equal to the addition of the last two numbers in the sequence. So we can see that based on the definition, we can have the Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And also we're assuming that if n is equal to 1 or n is equal to 2, then the Fibonacci of n will be equal to 1. Again, we're assuming that the first two numbers are 1 and not 0 and 1. So if you want to implement this like the definition the same way that as you see here, the Fibonacci of n minus 1 and plus Fibonacci of minus 2, we're going to end up with this like the simple recursive function. So for example, Fibonacci of an integer n, and we're assuming that n is a positive number, then if n is equal to 1 or n is equal to 2, we can return 1, and else we're going to return the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. If you run this program, we are going to actually see that the time complexity will be very bad, and it's going to be an exponential time complexity. Again, you can just watch my other video that I talk about that how and why this is the case. But let's just look at it from a different perspective and see that again why the divide and conquer is not working. Here's an example of the divide and conquer, because as you see here, we divided the problem, which is a Fibonacci, into smaller subproblems with n minus 1 and n minus 2. But honestly, if we look at the problem size of like the smaller subproblems, we have not actually made it much smaller. So the original problem size was n, so the input size was n. So here is our input size n. Next time when we're making the problem smaller, we're actually making it with the size of n minus 1 and n minus 2. And each of these will be n minus 2, then n minus 3, and here we're going to have n minus 3 and n minus 4. And as you see, we're just expanding each call to this recursive function. So we're not actually making it smaller, we're just like deducting 1 from the input size. So if you look at the ratio of the original input size to the smaller subsize, we have n over n minus 1 or n over n minus 2. So when n is a very big number, so when n is large enough, okay, then n over n minus 1, or maybe just write, maybe it was better to write actually this way. So let's write it n minus 1 over n and n over n minus 2 is very close to number 1. So it's very close to number 1. So in other words, it means that we have not actually made it much smaller. So, and as you see in this case, without actually making it smaller, we are doubling we're calling the function twice with almost the same size. So not making it smaller, not making it better, but actually make it the worse by almost calling the two sub-problems of almost the same size. Again, if you look at the ratio when n is big enough, okay, is much larger than 1, and again it is a positive number, and you see that this ratio is almost equal to 1. So again, not equal to 1 for sure, but it is very close to 1, which means that we're not making the problem smaller. So here again, we created two problems for the problem n. So as you see, we're trying to find, and the only the base cases are when we have n equal to 1 and n equal to 2. So this is n equal to 1, and here is n is equal to 2. As you see here, we need just to go down to these two numbers in order to find the Fibonacci for a number n. So here we have, starting with the problem with 1 call, then next time we're going to be 2 calls, next time it's going to be 4 calls, and there's going to be 8 calls, and there's going to be 16 calls. So as you see here, this pattern leads to the exponential time complexity of 2 to the power n, which is the very again solution, or the solution to this time complexity of this function that we have written here. So this is almost again 2 to the power n, which is exponential. So you can watch my other videos that I talk about how we can actually prove the time complexity of this version of Fibonacci is almost 2 to the power n. So we know that, so T of n, if it is the T of n is the time required to calculate the Fibonacci of Fibonacci sequence of n, then we have it is equal to T of n minus 1 plus the time required to calculate the Fibonacci of n minus 2. Also, we know that the T of 1 is equal to T of 2, and it is also equal to 1. Okay, that means that we just only need to have one if statement here, and we're just going to return 1. Either you can use 0 or 1. I think 1 is going to be actually we need to use 1 because it's a 1 operation, otherwise all the time it's going to be 0. So T of 1 and T of 2 will be called 1, means that we need to do 1 operation for each, and the rest will going to be calculated this way. So again, you can watch my video about how to calculate the T of n. As we know, that's going to be almost from the big of to the power n for the Fibonacci sequence this version. I'm going to also another example of the divide and conquer, and see that why it's working for other problems and not maybe for the problems like this that we're actually making or doubling this the size of the problem. So if you look at the binary search in a sorted array, so a binary search, so and here I'm going to write draw an array which is sorted. So let's say we have 10, 15, 18, 21, 24, 32, and 48. So here we have an array of 1, 2, 3, 4, 5, 6, 7. So n is 7. We have an array of size 7. And let's say we're trying to find x is equal to 10 in this array. Because the array is sorted, so we're going to start with like again n, which is our input size. And as you know, the binary search in a sorted array starts with the item at the middle, which is in this case is the number 21. And because 10 is less than 21, we're going to search only the first half of the array, or the left subarray of the original array. So as you see here, this time the input size n becomes n divided by 2. So we made the problem size half, and we're not searching the other half. So here, this one that we see here is not going to be searched. Next time, as you see here, the x equal to 10, so we're going to find the middle item here, which is 15. So, and because 15 is not the item and 10 is less than that, we're going to search even half of that. So again, this time n will become n divided by 4, n divided by 8, until we just reach to 1. And as you see, this is going to give us the big O of log of n. Again, you can watch my other videos about like the you know, these examples and why the time complexity because of log of n and to the power n. You know, the videos that are about the time complexity analysis and the way that, you know, we can calculate or find the t of n. So you know, maybe we can just generalize this, that if you know, maybe the ratio of like the problems that we're like doing is almost very close to 1, okay, and we are at least making like the double of that size, then we're dealing with maybe exponential time complexity. So that's but if you're just making maybe divided by half each time, we're actually working a better time complexity. Maybe we can also look at the sequential search as a very maybe example of the divide and conquer. So let's look at the above example that we had. So here's 10, here's 15, here's 18, 21, 24, 32, and 48. And let's say this time, so n is 7, and let's say this time we're searching for number 32, which is like the very second last item of the array. So at first we're starting with n equal to 7, which is just the size of the array, and we're searching the very first item. Next time, if the item we're looking for, which is in this case is not, so 32 is not equal to 10, we need to search the next item. So n this time becomes n minus 1, then it becomes n minus 2, then it becomes n minus 3, until it becomes like the 1. As you see here, we don't have any other branch, so there's only like the one smaller subproblem. So that's going to be from the big O of n. So if and in this case also the n minus 1 over n, again when n is greater than 1, like much larger than 1, is almost equal to 1. But again, as I said before, if you know, we have more than one subproblems and the ratio is equal to almost equal to 1, or we're close to 1, that means that we're actually making like this like the problem double, and we're not making it actually smaller. So it's going to be maybe exponential time complexity. Again, I hope that you can watch my other videos about you know, the time complexity analysis of like the Fibonacci sequence, also the binary search and sequential search, and how we can actually calculate the time complexities over the t of n for you know, any equation that we have.